You know, have you ever actually stopped to think about the screen on your smartphone? I mean, it produces these absolutely stunning, vibrant colors. But behind the glass, it is fighting this massive, invisible battle against a totally bizarre rule of quantum physics. It's a rule that severely handicaps the organic technology inside your phone. But, and here's the crazy part, it completely ignores the standard LED light bulbs illuminating the room you're sitting in right now. Welcome to this explainer. Today, we are unraveling a real technological mystery, the spin statistics paradox. To really wrap our heads around this paradox, we have to look at two completely different realms of lighting technology. First, we have the organic world. This is the realm of OLEDs, the beautiful screens in our phones and our high-end TVs, where everything happens at the level of localized individual molecules. Then, in totally stark contrast, we have the inorganic world. This is the domain of the standard, conventional LEDs, powering your desk lamp or your car headlights, where materials are structured in these continuous, sprawling crystal grids. So this brings us to the big question, the central mystery we are unpacking today. Does the strict, fundamental math of quantum spin statistics actually dictate how much light an LED can produce? Like, is there a hard mathematical ceiling on efficiency built right into the universe? Well, get ready for this because the answer is a massive double standard. For OLEDs, it's a hard yes. They are very strongly bound by a strict 1-to-3 quantum rule that we'll dive into in just a second. But for conventional inorganic LEDs, like those made from gallium nitride or gallium arsenide, the answer is nope, usually not. They bypass this specific limitation entirely. It's wild. So here is our roadmap for today's explainer. We'll start by decoding the OLED quantum math, then we'll see how brilliant engineers are hacking that 25% limit. After that, we'll cross the border to learn the inorganic world rules, check out some edge cases where spin actually still matters, and then wrap it all up with our final takeaway. All right, part 1, the OLED quantum math. Let's step into the organic world and see exactly what is holding our screens back. So in an organic LED, charge carriers aren't just flowing around freely like waves. Instead, you have an electron and a hole, and they meet up and actually get trapped together at a very specific localized molecular site. Now, each of these particles has a quantum property called spin, and when they bind together, kind of like two magnets suddenly clicking into place, they form an excited state called an exciton. This little pairing right here is the birthplace of OLED light. Now, the math behind this binding process works a lot like a quantum combination lock. When you combine two spin one-half objects, quantum mechanics dictates that there are exactly 4 possible spin combinations. One of those combinations gives you a state called a singlet. The other 3 combinations, they give you states called triplets. Assuming all combinations are equally likely to form, nature basically hands you a fixed ratio right out of the gate, 1 singlet for every 3 triplets. And wow. Right here is our massive fundamental problem. Out of all the excitons generated, only 25% are singlets. Nature is automatically hiding 75% of your potential light right from the jump. But why does that matter so much? Well, it all comes down to the fundamental rules of fluorescence. In a basic fluorescent OLED, that 25% of singlet excitons, they happily decay and emit light. We call that radiative fluorescence. It's great. But the remaining 75%, those triplets, are literally spin forbidden from emitting light directly. Because their direct emission breaks quantum rules, that trapped energy is overwhelmingly just lost as heat. Imagine buying a light bulb or, turning on your smartphone screen, where 75% of the power is instantly thrown away as heat, simply because of quantum statistics. That is the devastating 25% bottleneck that drains your battery. Which leads us straight into part 2, hacking the 25% limit. Because, let's be real, device engineers weren't just going to sit back and accept a 75% energy loss. So how do you cheat quantum mass? Well, they developed 2 completely ingenious workarounds to harvest those wasted triplets. The first is phosphorescent OLEDs, or FOLEDs. They literally sprinkle in heavy metals to create something called spin-orbit coupling. It acts like a quantum cheat code, breaking the rules to allow those dark triplets to emit light, pushing efficiency near 100%. The second workaround uses TADF OLEDs. These use ambient thermal energy to literally bump those forbidden triplets back up into the allowed singlet state so they can emit light normally. Just brilliant hacks, right? All right, part 3, the inorganic world rules. Let's cross the border over to the other side of our technology map to see how conventional room lighting operates. The core difference here is all about architecture. We are completely leaving behind the isolated, localized molecular cages of the organic world. In the inorganic world of crystalline semiconductors, particles are simply not trapped in little individual molecular boxes. Instead, electronic states in traditional LEDs exist as what we call extended block states. Think of it like a massive, wide-open highway system instead of a bunch of isolated single-car garages. Electrons and holes exist in continuous, sprawling energy bands. This structure natively includes spin, orbital angular momentum, and crystal symmetry right out of the box. So that entire dynamic of isolated molecular pairs and that strict 1 to 3 singlet triplet counting game is entirely removed from the equation. And because nobody's getting trapped in those molecular excitons, producing light here isn't about counting singlets and triplets at all. Instead, it's all about band-to-band recombination. An electron up in the conduction band drops down to recombine with a hole in the lower valence band, and bam, it releases a photon. The question scientists ask isn't, is this a singlet or a triplet? The question is just, is this transition optically allowed by the open highway of the band structure? So if that pesky 25% rule doesn't apply here, what actually limits a standard inorganic LED? Well, it really comes down to physical material engineering. Instead of fighting fundamental quantum spin rules, engineers here fight physical imperfections. They obsess over eliminating tiny material defects in the crystal and optimizing how the electrons flow. As long as the physical crystal quality is super high, efficiency can be incredible without automatically losing 75% of your carriers to some forbidden triplet reservoir. Now for part 4, where spin still matters. Because we do have to be precise here. Saying inorganic LEDs bypass the 1 to 3 rule doesn't mean quantum spin just magically disappears from physics entirely. Let's look at a couple of edge cases. Take quantum dots or 2D semiconductors, for example. When you take inorganic materials and subject them to extreme confinement, literally trapping them in tiny nanostructures, they actually start behaving a bit like molecules again. They recreate strong excitons, which split right back into bright excitons that emit efficiently, and dark excitons where emission is forbidden. So spin statistics absolutely matters again there. We also have spin lids, where scientists deliberately inject spin-polarized carriers just to emit specifically polarized light. So spin physics is universally important. It's just applied completely differently depending on the structure you've built. Finally, part 5, the final takeaway. Let's bring this whole story together into one unified picture. This master matrix pretty much perfectly sums up our whole journey today. For fluorescent, fold, and TADF devices, their organic molecular nature means they all operate under the strict 1 to 3 singlet triplet math. They just use different engineering hacks to handle the fallout. But jump over to the inorganic direct gap LED column, and poof, that 1 to 3 rule vanishes, replaced natively by continuous band-to-band transitions. Which brings us to this perfect, definitive quote from our source material. OLED efficiency is often spin statistics limited. Ordinary inorganic LED efficiency usually is not. It is such a fascinating divide, isn't it? Our displays have to use these brilliant chemical hacks to cheat quantum mechanics, while the lights on our ceiling just coast right past the rules thanks to their crystalline structure. Honestly, it makes you wonder, what other invisible fundamental quantum rules are secretly shaping the design of the technology we carry in our pockets every single day? Thank you so much for joining me on this explainer, and hey, keep questioning the science around you.